Hi everyone. In this video, I will state the first law of thermodynamics, and then I will show you how to use this equation: eternal energy equals heat plus work. Alright, as we continue our discussion on energy in reactions and processes, let me first give you a couple of definitions. The first one is thermodynamics. Thermodynamics is the study of energy and its conversions. But you recall from the previous video that a subset of thermodynamics is actually thermochemistry. One definition of thermochemistry is the study of energy transfer. In particular, thermal energy, or heat. In chemical reactions and processes. The abbreviation for reactions from now on will be RxN, and processes. Okay, now that we have a broad definition for thermodynamics, let me give you the setup so we could talk about the first law of thermodynamics. And we actually do want to talk about first the law of conservation of energy. You might have heard of this before. Energy can be converted to one form or another, but it cannot be created or destroyed. Energy can be converted into one form or another, but it cannot be created nor destroyed. Now, the first law of thermodynamics is an application of this conservation of energy law. And many times the first law of thermodynamics can be simplified into the total energy energy of the universe is constant. I know we're doing a lot of definitions. We'll get to the equations in just a bit. Now, you might have heard of Einstein's equation E equals mc squared. That still applies. That still is true. E equals mc squared. Energy, mass, times the speed of light squared. Because the law of conservation of energy accounts for that, because energy can be converted into one form or another, but it cannot be created or destroyed. But for most chemical reactions that we'll see, we're going to conserve energy and mass independently. you will conserve energy and mass independently. Okay, now, because of this idea that the total energy of the universe is constant, what we can derive, or what follows, is this, and we'll put this in green. Delta U of the system equals the negative delta U of the surroundings. And let me put that in a box. Basically what this says is that any energy that's lost by the system will equal the energy gained by the surroundings, and any energy that's gained by the system will be equal to any energy, the same amount of energy lost by the surroundings. Also, if you rearrange this, then that means that the delta U of the system plus the delta U of the surroundings equals zero. Now, we talked about in the first law of thermodynamics the energy of the universe being constant, and in thermochemistry, energy transfer. I want to go over a little bit how energy is transferred from system to surroundings and vice versa. Here on the left, I'll have system, and on the right, I will have surroundings. There are two ways that energy, in particular internal energy, can go back and forth between the system and surroundings. The first way is via heat. And the symbol for heat is going to be Q. The other way that energy can be transferred between the two here are by work. And work abbreviation is W. So the next equation, and we'll actually use this in an example, is the change in internal energy. And you could assume that they mean the system is equal to the heat plus the work. Now, all of these terms are energy terms: heat, work, internal energy, meaning that most likely you're going to be working with the units joules. Joules or possibly kilojoules. All right, first example, and how we're going to apply numbers to this equation. We're going to look at what's called a potato cannon. And basically that is a tube closed at one end, open on the other, and you put gunpowder at the bottom, and a potato. What color am I going to use? A potato plugging up the hole. And the idea is to spark your gunpowder through a tiny little hole, create enough energy to blast this potato out of the cannon. So what's important when we're given a problem, especially if we know we're going to use this equation, is make sure that you understand what the system is and what the surroundings is based on the question or your professor. So let me give you the setup. Where am I going to put this? Here. If the burning of fuel performs, let's say 855 joules of work, and produces 1422 joules of heat. What is the change in the internal energy of the system? And I'm going to say, internal energy change of the fuel is a better way to put this. So that's unambiguous. The system is going to be the fuel, and the surroundings is everything else. So what could that be? That could be the air, which will expand upon explosion. Okay, the air that will get heated upon explosion as well. It could be the potato that would now have kinetic energy flying out of the cannon, etc. Anything else besides the fuel. Okay, we have two numbers. You want to make sure that you know what's given. We have this number and we have this number. And you want to know what is being asked. And typically I put a question mark, and they want the eternal energy. Not only do you want to know what the question is asking for, but also what units the grader expects. And this is going to be in joules, right? Because the heat and the work are given in joules. Okay. Before we do this problem, we got to understand what signs will be applied to these values, negative or positive, and let's make a table of signs for both Q and W. Okay, in red, if your question states that the system releases heat, well, that means the energy of the system in the final state is less than the energy in the initial state. So that means if you do final minus initial, you'll get a negative number. And yes, if the system releases heat, Q is negative. But if the system absorbs heat, I'll put it next door. System absorbs heat. Q is positive. The final state has more heat than the initial state. What about the work? I think work is the one that sometimes trips people up. If work is done by the system, work is done by the system. So the important words are by the system. Then W is negative. It does work. It expends energy to do that work. But if work is done, what's the opposite of by the system? If work is done to the system, and the main words there are to the system, W is positive. Okay, so there's your table of signs. Of Q and W signs. You're going to use that table, okay? Hopefully you can rationalize why Q is negative or positive in these cases and why W can be negative or positive in each of these cases. And you're going to apply that table to these numbers and to this equation. Okay, do you want me to put it all on one screen? How about that? And you're going to answer what is the internal energy change right there. Okay. You could pause the video if you want. I'm about to answer this myself. Answer what is delta U using these signs conventions. Okay. Go ahead and jot down an answer before you see how I would do it. Okay. When in doubt, or when I get nervous on exam, I like to write down the equation, even though it seems pretty simple and I can memorize it. Just seeing it assures me a little bit better. And I have heat. Now the heat they told me was 1,420 joules of heat produced. Produced means released. So that's a negative number. In my work, delta U equals negative 1422, a negative Q. It says that the fuel, upon burning, performs this much work. It does the work. The work is done by the system. 855 by the system. So this is minus 855. So therefore, delta U equals a large negative number. 1422 minus 855 minus 2277. Make sure you put the units, joules, and make sure you circle your answer so the grader can find it. Make sure it makes sense also. Again, the burning fuel performs or does work, and it does work by producing heat or releasing heat. Okay. Take a look in your textbook for other examples. You could do these examples. Here's a potato cannon, but what about an expanding balloon? Or what about a fuel that's pushing the plunger of a piston in a crankshaft? There are multiple examples where you could practice internal energy change equals heat plus work.